Hi everyone, in this video I am going to decode and solve some problems that relate to heating and cooling curves. These are the problems that tend to give students fits, and they do require using the reference table, this portion of it, and this portion of it. They'll be extremely helpful, as I hope this video will be. So good luck. So here's the first sample problem, and let's decode it. It says, how much energy is required to completely convert 10 grams of ice to liquid water? So to completely understand this question, I must look at this map. And we are going from ice to liquid water between these two states here. And I notice that I do not have a temperature change here, so I'm not going to be using the formula that has the delta T. But what I am going to do is I'm going to use the formula that involves the heat of fusion. And what always helps me understand that is we have another formula with heat of vaporization, and vaporization always makes me think of gas, which is here. So the heat of vaporization formula lives right in here. So we must be using the heat of fusion. Now let me write that one for you. It's Q is equal to mH. Now, if you were to have forgotten that that's the formula we're using, perhaps looking at the reference table would have assisted. And in inspecting our reference tables, we would notice here are our options, and hopefully by looking at the options, it rings a bell for you. So we need to actually do the math of this problem, and for that I'm going to write down what I know and my unknowns. So what are my knowns and my unknowns? So what do I know? I do know that my daughter is eating a gingerbread house as I do this, so if I don't get distracted, we'll know why. I do know that I have a formula of Q is equal to mHf. I know that the mass is equal to 10 grams. I know HF. I do know HF. Now I know HF because it is a constant. And a constant is a value that never changes. It is well known for water that heat of fusion is 334 joules per gram. So that's 334 joules, a value of energy needed for every 1 gram of water. So 334 joules per gram. I got to remember that. 334 joules per gram is equal to HF. So now I can solve for the unknown, because the unknown we are solving for is Q. So Q is equal to the mass, which is 10 grams, times 334 joules per gram. Now what happens here, I want to focus on the unit for a moment, is I've got grams on a numerator and grams on a denominator. Grams divided by grams, they go away, leaving me with 10 times 334 joules, which is going to be equivalent to 334 joules of energy necessary to convert. Needs to be absorbed by the water, or the H2O, needs to be absorbed in order to convert it from gas, right, from ice to liquid. And I was just distracted by this little one here. Say hi.
Hi.
Okay, we'll move on to the next question in just one moment. So let's decode this next question. How much energy is lost when 10 grams of water vapor completely condenses to liquid? So, excuse me, we're going from vapor to liquid water, and it is losing energy. So we are going from here as a gas to here, and it is losing water. So we're actually, it actually should look more like this, but let's not worry too much about that. So what happens here? We are going to be using the formula of Q is equal to the mass times HV. Now again, we're still using HV because even though we're not vaporizing, it's still the same amount of energy in reverse that will be released. So let's go ahead and do this equation. Write down our knowns and our unknowns. Our known and our unknown. We do know that we have the formula Q is equal to mHV. We do know that our mass is 10 grams. I'll show you in one moment what HV is. We're solving for Q. So HV is again one of those constants. And let's inspect. HV now tells us that heat of vaporization, it is required that we have 2,260 joules for every 1 gram of water to convert it from liquid to gas. So 1 gram of water going from liquid to gas requires 2,260 joules of energy. Let's get this out of the way. Oh, what was that number again? 2260. This is equal to 2260 joules per gram. Yes, thank you, sweetie. Put some water in that, will you?
I did.
Okay. So Q is equal to 10 times 2260 joules per gram. Now, just like the last slide, when we inspect the grams, grams divided by grams, they're now gone. And what are we left with? 10 times that value. Please step. Which is 2260. Because we're timesing by 10, add another 0. We've got 22,600 joules of energy. Now, just so you know, that could also be written as 22.6 kilojoules, because kilo means 1,000. So we can create a shorthand where it's 22.6 kilojoules of energy required, which is lost actually, when 10 grams of water moves from gas, a vapor, to liquid. So it is losing this amount of energy. And if it's losing that energy, let's also consider it is an endothermic reaction. Now here's the third type of problem I want to discuss with you now. And it's decoded in this fashion. How much energy is absorbed by 10 grams of liquid water when it changes from 30 degrees Celsius to 40 degrees Celsius? So where on this chart, this graph, are we talking? It's saying that it is changed from 30 degrees to 40 degrees, and 30 degrees, well, this is solid down here, liquid and gas. We know that this is 0 degrees, this is 100 degrees, so 30 and 40 would be in here. So our formula lives in there. And if we're having a change in temperature, we are going to be dealing with the one that deals with change in temperature. Q is equal to mc delta T, because delta T is a change in temperature. All right, so let me clear the screen here, and we'll proceed. All right, so known and unknown. We know that we are going to be using Q is equal to mc delta T. We know that the mass is 10 grams. We know what C is. I'll show you right now what C is. C is the specific heat capacity for a substance. In this case, we're dealing with water. And the specific heat capacity for water is 4.18 joules per every gram of water that is increased 1 Kelvin. Now, we have to remember that every single time we increase or decrease 1 degree Celsius, we are changing the same amount in Kelvin. So 4.18, let's remember that. So 4.18 joules per gram degree Kelvin. What we do not know is Q. We're solving for Q, the amount of energy. And at this very moment, we do not know delta T, but we will get that in a moment. We know that back to the known side, Trisha, please stop. We do know that we do have one temperature, which is, well, we're starting at 30, going to 40. Our initial temperature is 30 degrees Celsius. Our final degree temperature is 40 degrees Celsius. So let's first investigate that, because change in temperature is equal to T final minus T initial. So the final temperature is 40. And right here, let me just change it to Kelvin, because if it's 40 degrees Celsius, actually I should not do that, because that is not equivalent. Let's just say 40 degrees Celsius minus 30 degrees Celsius. That's very loud. Stop it, please. The change in temperature is equal to 10 degrees Celsius. And as I said a moment ago, every single time you change 1 degree Celsius, you're changing 1 degree Kelvin. So our delta T is actually 10K. So how can we use this? Well, we do know now that that is 10K. So it moves over to there. All right, so Q is equal to 10 grams times 4.18 joules per gram degrees Kelvin times 10K. And let's inspect the units. We've got grams divided by grams. We've got Kelvin divided by Kelvin. Our last unit standing is going to be joules. So what is 10 times 10 times 4.18? It is 418 joules. So that is the amount of energy that will be required to be absorbed by the water to make it change from 30 degrees to 40 degrees Celsius for 10 grams of that water. So there you go. I chose 10 grams each time for the mass, because just so that it would be easier for me to do the math in my head. But please use a calculator when those values are not easy to manipulate in your head or on paper. Good luck with the rest of the problems.